Hi, it's Kate, and this is the fourth video for Fortnight 7 of Math 23B. We're going to continue on combining various issues that we've learned about over the year, and this topic is a combination of sequences of functions as well as integration. Before we jump right into it, there are a couple key terms that we do need to clarify before getting into the thick of things. The first is measure zero. We say that a subset of Rn has measure 0 if for any epsilon greater than 0, this set can be contained in the union of an infinite sequence of open boxes whose total volume is less than or equal to epsilon. Now, a lot of people look at this and they say this sounds a lot like a set of volume 0, but in fact it is not. Remember that volume 0 is a set that can be covered with a finite covering of open boxes whose volume is less than epsilon. So measure 0 allows for this to occur, but using an infinite sequence of open boxes. So for instance, when we look at the rational numbers in the interval from 0 to 1, this has measure 0 because we could make a tiny box over every single rational number which can be enumerated. That would be an infinite sequence of open boxes, and make those boxes as small as we like, so the total volume can be made less than or equal to epsilon. But note that it does not have volume 0. We can't achieve this using a finite number of boxes. Because if we're stuck using a finite number of boxes and we tried to shrink them down so those boxes have a total combined volume of less than epsilon, the problem is that we can't actually shrink them, right? Because there are so many rational numbers in that interval that they would have to have a combined volume that was greater than some epsilon, based on the fact that there are so many of them across the entire interval. And in fact, in every subinterval, you can find a rational number, just as we did in the first semester. So that's the difference between measure 0 and volume 0. Measure 0, you can use an infinite sequence of open boxes with total volume less than epsilon. Volume 0, that's a finite number of boxes with total volume less than epsilon. Why is this concept important? Well, we're going to combine the idea of infinite series and integrals, because the notion behind this is that we know that the sum of any finite number of Riemann integrable functions is integrable. What if we had an infinite number of Riemann integrable functions? Could we still make that integrable? A Lebesgue integral does exactly that. It extends this idea to a function that's the sum of an infinite series of Riemann integrable functions. And so what we're looking at is we say, okay, suppose we have this function, and the way we can actually express this function is as the infinite series of a bunch of different functions in a sequence. So each of these functions, f sub k, are tiny pieces of functions. And what we're instead looking at is, when I'm looking to integrate, can I compute this? Can I say, okay, if I took the integral of each of these functions in the sequence and then added them together, created an infinite series of integrals, would I be able to evaluate this to a finite value, some value a less than infinity? And in fact, you can. That's exactly what Lebesgue integrals are. Now, you'll see in class that the sequence of functions is a little convoluted. Sometimes they're specifically constructed to sort of piecewise divide up a continuous function that happens to be unbounded, or perhaps unbounded function or an unbounded interval. It depends. But this is the basic idea, that we're trying to figure out if we're able to evaluate this infinite sum of integrals. So the idea is that if the above here is holding, then we know that the function f is defined, except perhaps on a set of measure 0. So in that sense, that means that the sequence of functions, if we added them together, if we added all of those functions together, it does converge to some sort of parent function. And the quantity here that we've managed to compute up here defines the Lebesgue integral of this function. Note that this is absolute convergence of that series, which is more rigorous than allowing it to possibly take on some negative values over each of the f sub k integrals. If you have a function f that's equal to an infinite sum of f sub k's, and you have a function g that's equal to the infinite sum of g sub k's, so each of those parent functions are the product of a sum of an infinite number of f sub k's or g sub k's, and both of those are equal except on a set of measure 0, then their Lebesgue integrals are also going to be equal when we set about computing this for both the f's and the g's. Note that if f is Riemann integrable, then its Lebesgue integral is going to equal its Riemann integral. That value will not change. So it's not super valuable, though, to talk about the functions that are Riemann integrable and how their Lebesgue integral is equal to their Riemann integral, because the whole point of Lebesgue integrals is that they actually can compute integrals in situations where Riemann integrals fell short. So there are a lot of functions that are Lebesgue integrable that are not Riemann integrable, and that was the whole purpose of sort of devising this approach. Note that, remember, Riemann integrals fell apart when we encountered an unbounded function. So for instance, this function from 0 to 1 of 1 over the square root of x can be rewritten as an infinite sum of Riemann integrable functions. So the way we do that, I'm going to fix this typographical error, but the way that we do that is each of the f sub k's is going to be equal to 1 over square root of x, but only on a very small interval, as we're sort of nearing this discontinuity, the asymptote, as we approach 0. And so each interval, that's really what the k is affecting. We're only looking at the function at a very small interval as we're getting closer and closer and closer to 0. And everywhere else it's equal to 0. So each of the f sub k's individually has an integral that exists, and we're hoping that by summing together all of the f sub k integrals will have some series that is going to converge. Another example of a function that doesn't have a Riemann integral is this one right here, e to the negative x, because it has unbounded support from 0 to infinity. Right? We need this to be finite in order for it to be Riemann integrable. And instead, with Lebesgue integration, what we can do is, well, each of the f sub k's, each of the functions in the sequence that will contribute to computing this integral will be e to the negative x, and the interval will go from k to k plus 1. So you can see that each interval is length 1 in this particular case, and we're going to see whether or not this particular series of each of the tiny integrals along these slices, so to speak, converges. Whereas these subintervals get smaller and smaller and smaller and smaller, handling the asymptote as you're moving towards 0. We also have the example of the function that's discontinuous at all rational x, where the function f equals 1 at rational x and 0 otherwise. That can be written as an infinite sum of Riemann integrable functions, with f sub k equaling 1 when x is one specific rational number, x sub k, and then 0 everywhere else. So those are some examples of functions that are Lebesgue integrable but not Riemann integrable. That's the idea behind Lebesgue integration. It fixes this problem of not being able to deal with an unbounded integral or an unbounded function at a particular point in the interval. And you'll do a few examples in class, in the small group problems, and on your homework to see how these particular Lebesgue integrals are extremely useful to us as we're trying to integrate more and more functions.